So what I would like us to do here with these parent functions, again, before we get into like increasing, decreasing, and zeros and stuff like that, I do want to kind of list the basic, domain and range of these parent functions, so that way when we see transformations of it, we can maybe more easily identify, how the domain or how the range is going to, kind of adjust accordingly, right? So we'll just go through that here real quick. Shouldn't take too long, all right? And we'll kind of maybe just call in some folks here to help us out. So let's go to Kayla. So Kayla, for number 1 here, this identity function, maybe I'll do this in a just slightly different color, okay? What would the domain for that function be? Yep, negative infinity to infinity, exactly right. Okay, so any shift, left or right, still is going to be domain negative infinity to infinity. And again, we shouldn't, be surprised by that. It's just x. There's no dividing by a number. There's no square roots here. So the domain should be just all real numbers there. What about the range here, Kayla? What would that be? Yep, negative infinity to infinity. So again, any vertical shift, right? Any shift up or down. So if we add something to the x or subtract something from the x, we would still expect the range to be negative infinity to infinity. So lines, nice and easy. Okay, with those adjustments and things. Okay. Let's go to Julia I in the back there. Okay, how about the absolute value function, Julia? So the domain for that would be what? Negative infinity to positive infinity. Exactly right. Okay, because again, there's no possibility of dividing by 0 here, right? There's no square root or even powered root of a negative that we could take. And so any x value can go in there. How about the range, though, Julia? What would that be? 0 to infinity. And do we include or exclude that 0? Include. That's right. We do get there, right? You plug in 0 for absolute value of 0. It would give you 0. So we do have that there. Okay. So now here, right, unlike the graph of x, since our range is other than negative infinity to infinity, now those vertical shifts, right, are going to affect that range. If you shift things up, then your range will also be, adjusted accordingly, shifting up or down. We also want to be careful, right, if you throw a negative in front of that absolute value, right, if you had like negative absolute value of x, that would reflect it, and then also that would adjust the range, right? So if you reflect that down, it will be then negative infinity up to 0. Okay? So be aware of that too, right, those adjustments. All right, and let's look at the square root of x here, and let's see. Let's go to Noah. So Noah P in the back there. Okay, so what would our domain be here? What's the leftmost x value that we can, kind of hit? 0. Yep. So we'll start with 0, and we'll include it, and then it goes to infinity. That's right. All right, and then what about the range there? Noah, what would that be? Again, what's the lowest y value that we hit here? 0 as well, that's right, including it, and then off to infinity. Okay. And so here, right, both left and right shifts, right, so a shift left or right would result in a change in the domain. A shift up or down will result in a change in the range. You also want to be watching about, reflections and stuff too. And we saw one like that. We saw one like that on the warm-up. Okay, so that's that. Very good, Noah. Thank you. All right, bless you. Yes, let's go to. Just want to make sure. Yeah. Okay. Let's go to Nick. Okay. So Nick, how about this one? What's our domain here, sir?
All real numbers.
Okay. All real numbers. Negative infinity to infinity. Very good. And how about that range?
Y is greater than or equal to 0.
And if you'll permit me, I'm just going to use the interval notation. But you're right. Y is greater than or equal to 0. Very good. Again, similar idea. So this x squared is a similar kind of idea to the absolute value of x, right? Shifting things left or right is not going to affect the domain, but up and down will affect the range. Okay, and also then reflections and stuff. You want to look out for that. Okay. Good. All right, another one here. Let's go to Colin. Okay, so Colin, what do you say here for the domain?
Negative infinity to infinity.
Negative infinity to infinity. Again, very good. No possibility for square root. No possibility for a square root of a negative. No dividing by 0. And how about the range? What's that going to be? Negative infinity to infinity. Yep, very good. All right. So shifts here don't affect anything, right? Basically, a cube will always be you know, negative infinity to infinity, negative infinity to infinity for both situations there. All right. And then finally that rational function, right? The one that's kind of like the newest or the least familiar. And we'll go to Robert there in the back. So Robert.
Negative infinity to 0, union 0 to infinity.
Okay, so yeah, negative infinity to 0, union 0 to infinity. Very good, Robert. Yep. And then how about that range?
Negative infinity to 0 and union 0 to infinity.
Negative infinity to 0, yep, union 0 to infinity. Exactly right. So just excluding those zeros, again, or adjusting that depending on the shifts. Okay, or adjusting that depending on the shifts. All right. So there's that, just maybe to help you out now. Okay, should you maybe this is additional information that maybe will help you with adjusting your adjusting your domain and range values. Really, the domain is not such a big deal because you know you don't need to like worry too much about the domain. Again, as long as you follow the two things, right, that we need to check when we divide by 0, right, and we exclude those numbers that make us divide by 0, and we also exclude anything that would make us take the square root of a negative as well. So that takes care of the domain. These are more for the range, right, because the range we don't have any like range restrictions that we're looking for. It's really just the shape of the graph and how it kind of works. So there it is. Okay. Questions on any of that? All right. Then let's get into here what the rest of what I wanted to do today. Now that we've had that little preliminary thing there. All right. So today we're just going to add on a little bit more to our function behavior analysis, right? Stuff that you've seen before, right? And maybe this is even, you know, more ingrained than some of the other things we've talked about, right? So I'll call this like function characteristics, and specifically we're going to be looking at zeros, and then increasing, decreasing, and constant behavior. Okay. So taken individually, these function characteristics aren't too terrible, you know, but then when you start just throwing it all together, that's where it can get confusing. So we haven't done that yet, right? But, you know, individually these pieces maybe are less intimidating, but then it's when it's like, you know, it's like, wait a minute, is this the place where I'm supposed to set it equal to 0, or I'm supposed to take the bottom and set it equal to 0, or like, it gets confusing. So that's why, you know, we go through in pieces, and then eventually we'll put this all together and stuff too. So we'll start out talking about zeros, okay? So a 0, or a root, right? Or you can say like an x-intercept. Okay. These are all kind of like synonymous with one another, I would say. All right. These are just points where the function crosses the x-axis, or intersects the x-axis. Points where the function intersects the x-axis. And I guess saying crosses the x-axis isn't always very accurate, because you could kind of have your function come down, just touch the x-axis and go right back up, right? It doesn't have to go through the x-axis. It's touching it. Okay. But notice here, right, a 0, right, does not include a y-intercept. So if I ask you to find the zeros, you don't need to list the y-intercept there. I mean, if you do, that's okay, but a 0 really is just talking about the, normally talking about the x-axis, or x-intercepts. Or the roots, too, same idea. All right, so, and again, this isn't going to be too mind-blowing here, but to find a 0, okay, again, or root, or an x-intercept, well, we're going to set the function equal to what? 0. Yeah. No surprises there, right? Set the function equal to 0. You know, if we think about like what's the thinking, what's the concept behind that? Well, again, if we're looking for points that are these, either 0, roots, or x-intercepts, in other words, we're looking for points where the function intersects the x-axis. Well, one fact that we know about any point on the x-axis is that its y value, its y-coordinate, must be 0. So by setting the function equal to 0, we're saying, okay, the y value, the function value, must be 0, and then let's just set it equal to 0, and set that function equal to 0 to find the x values that result in 0. Okay, so we're going to set the function equal to 0, whoops, I'm going to add something here, and solve for the variable. Okay, set the function equal to 0, solve for the variable, because again, think about what you're trying to find. When does it cross the x-axis? It's a y value of 0 on the x-axis. Alright, so we'll jump into an example here. Let's find the zeros of, okay, and let's see here. The first function here, f of x equals, excuse me, x squared minus 5x plus 6. X squared minus 5x plus 6. We want to know, when does this thing cross the x-axis? All right, so we'll set it equal to 0. Okay. And then at this point, what should we do here? Yeah, Devin? Okay, you want to subtract 6 from both sides. Okay. So that's gone. We're left with, I don't know why I wrote the minus 6 like that. Sorry. All right, and then what do you want to do? We could factor an x out here. So now I have that x times x minus 5 has to equal negative 6. Okay, and so we may be tempted to say that, oh, well, that means then that x has to equal negative 6 or x minus 5 has to equal negative 6. But that's not necessarily true, right? Just because we have two things that multiply to give us that negative 6 does not mean that one of these two things has to equal negative 6, right? For example, if I had, if this was 2 and this thing was equal to negative 3, 2 times negative 3 would give me negative 6. And so saying that if these two things multiply and give me negative 6, I can't guarantee that either the x has to be negative 6 or the x minus 5 equals negative 6. There's only one number that if you are equal to that number, if two things multiply to make this particular number, then one of those two things has to be that particular number. Yeah, Emma? Yes. And that is very important. It's important that we keep this equal to 0 here, because we're going to factor it at that, we want to factor it right now, well, back to where we had it here, up equal to the 0. Okay. I was like, Mr. Widmeyer, why would you write that down? I have to erase it. Okay, well. Okay, exactly right, though, Emma. Yes, we want to just keep it equal to 0 so we can use that 0 product property, because 0 is the only number that has that special property. If two things multiply, or two or more things multiply to make 0, one of those things has to be 0. Okay? So Devin, thank you for being a good sport too, though. I appreciate that, because I wanted to use this as an opportunity. You're not the only one that did that, so I'm sure. So I appreciate that. Anywho, yes, factor it. Emma, can you factor it for us? What does it factor be? Very good. Yeah. Okay. Again, for those of you that have your different little factoring techniques, I know some people use like the magic X, right? Or some people have other like cutesy names for it and stuff like that. When I learned to factor, I just did basically like a guess and check thing, where I was like, I know I need two numbers that multiply to make positive 6, but then add to make negative 5, and I would just sit there and write down some numbers, and then I'd get it wrong, and I'd erase it and keep going, and it was torture. But that's how I learned it. So anyway, now we have two things that multiply to make 0. That means one of those two things must be 0. There's no other way to get 0 when you multiply. Okay, as So now we are allowed to do what we wanted to do earlier. So we have x equals 3 and x equals 2. Okay, so let's see here. This is wrong, just right there. Bless you. Everything else we did here is mathematically like okay, right? It's not wrong. It just wasn't helpful. We weren't able to use the information here. We wanted to keep it equal to 0. So this is really the path we wanted to take because it resulted in us being able to use those zeros. Okay. 3, 0, and 2, 0. All right, so those are the zeros. All right. Very good. Well, let's try another one. H of x equals 3 over x squared minus 9. And we'll also spend some time going back and looking at factoring too. So if like, you feel rusty on factoring quadratics and stuff, we will spend some time, like relearning some strategies and stuff like that there. So don't fret, too much. Okay. Okay, so we want to know when where the zeros are for this function. So let's go ahead. We'll set this thing equal to 0. All right. So we want to know when that thing equals 0. So the idea is here. When does this equal 0? Okay.
Can I say zeros or should I just say how to do it?
Yeah, go ahead. Let's say how to do it. What would you do? What would you do here?
I would factor the bottom to be x plus 3, x minus 3.
Okay, factor the bottom to be x plus 3, x minus 3. So yeah, that is a difference of squares. That's right. Okay.
And then what is your 0 to be minus 3 and positive 3?
Okay, so x equals negative 3 and x equals positive 3. So let's just start with that negative 3, for example. If I were to plug, it would be divided by 0, which is undefined. So you found the domain restrictions, not the zeros, right? So yeah. So good thinking, though. That's important to know, too. So what would give us 0 here, then? When does this thing equal 0? When does this equal 0? Okay, let's see here. So if I plug in 1, it will be, I'll plug it up here because maybe it'll be a little bit easier. 1 squared, okay, is 1, minus 9, negative 8. 3 divided by negative 8, that's going to give us negative 3/8. Or if I put in the negative 1, same thing, negative 1 squared will be positive 1, minus 9 will still be negative 8. So yeah, no, that's not going to work. That'll give us a y value that's other than 0. So again, where does this thing equal 0? For what x value does it equal 0? Yeah. What do you mean by that? There are no zeros. That's right. None. Okay, it's kind of a trick question there, right? All right, but there are no zeros here. Very good. No zeros. Now let's think about why that might be here, right? So obviously we could graph this, and we could just like visually see that this particular graph will never cross the x-axis. But another way you can think about it too, just looking at the function. This thing is really just a fraction, right? Like kind of like a glorified or more complicated fraction, than just like 3/4. Okay. A fraction can only ever equal 0 when what part of that fraction equals 0? The numerator, the top. Exactly right. Our numerator here is 3, and it will always be 3, and so there is no opportunity for this to ever equal 0. Okay? The denominator, absolutely, it can change its value. It's going to change, depending on what x value you plug in, but the numerator will always be 3, and there's never a chance for it to equal 0, and so that's why there's no zeros there. Okay? So, which is good because in the future, right, if you see some sort of complicated rational function like this, you only need to worry about the numerator, when the numerator equals 0. Okay, and so I'll put a little note of that here too. Okay, for rational functions, okay, that is, like f of x over g of x kind of deal, right? A function over a function looking thing. Okay, for rational functions, set the numerator equal to 0. To find zeros. Okay, and so here's a place where lots of students get, two things mixed up because they're so similar, right? When you have a rational function, that is, kind of something over something, there's two things you can find by setting two different things equal to 0. When you set the denominator equal to 0, that means you're looking for your domain restrictions, right? Denominator equals 0, that means it's going to be undefined. But setting that numerator equal to 0, that means you're finding when the fraction overall has a value of 0, which means you're finding the zeros. So numerator equal to 0, zeros is what you find. Denominator equals 0, you find domain restrictions. Okay, and that's one of those ones that I know students get, mixed up and stuff like that. Okay? All right. Enough of me. We're doing the work here. You guys are going to try one. So you guys try g of x equal to the square root of 2x plus 5 over x minus 2. And then I also want you to try, so that's, I guess, number 3 in this case. And then I also want you to try m of x equals x squared minus 2x all over x cubed plus 3x. Okay, and again, just find the zeros. That's all we're doing here, finding the zeros. You don't have to worry about, domain restrictions. Well, sorry. I'm not asking you to find domain restrictions here. Just identify any zeros. Okay? But you do want to maybe consider domain restrictions as well here. You want to consider, I'll say that much. You do want to consider domain restrictions here. I'll come around and help here as necessary in just a second. Well, you can undo this square root. Once you set that up, you can undo it, right? Right. Yeah. Okay, but good. You fixed it. Good. So now you're going to try the second one. This is over 4 then? Okay. Yeah. Okay. Good. Yeah. That's, I mean, that's correct. Very good. But yeah, of course, that's the right. Absolutely, yes. Correct. Yes, those would be the solutions there for that equation. But then you also have to look at your domain restriction. Wow. For that function. Second one, yeah.
Right, because then it would be equal to 0, yeah.
So right now it's equal to 0. So we want to use that to our advantage, right? Because we want to use that zero product property. So you don't want to move stuff. But what can you do between these two things? There you go. And now you have a product of two things that multiply by 0. You can set each one of those things here to 0. Yeah. But then you also have to go through the domain restrictions of that function, which I know we didn't really do in previous problems, but in this case you really need to pay attention to that. Look at your domain restrictions. This is right, and these, those are right, but check your domain restrictions because I see a conflict. So it's not oh, just because. Oh, okay. I apologize. Any general questions? Yep. So have you identified them? Not yet. Okay. So look at those, and then you might see a conflict. What you've got, and then yes. Yes, that is exactly what you should do. Yes. Yes. Well, so if you have two things, right, x and x minus 2, they're multiplying and they equal 0. So using that zero product property, that means either x has to equal 0 or x minus 2 has to equal 0. Well, careful. It won't be -2 that you subtract 2 to give you 0. It'll be a positive 2. Right. So then you identify the one will be what? X equals. Well, you have two things that are multiplying to give you 0 here. X means either x is 0 or x squared plus 3 equals 0. Right, the domain restriction, so that would give you right?
You only get one for both.
Yeah.
And well, I got 2 for the second one. This is the second one? How do you put it? Well, one of them didn't work. It's 2.
Oh, I think you got 2 answers.
No, like 2 and 0.
Oh, sorry. 1 to 2. So look at your domain restriction. Compare that with your there may be a conflict
Because that's for 0, and you divide 0. You divide 0 by 0.
Okay. Just give you like 30 more seconds here, and then we will go over this. Okay. Let's see here. Let's go to. Oh, that's funny. Lindsay. So Lindsay, how about for that first one, number 3 there? What did you get for your zeros?
I got -5 halves.
Negative 5 halves. Okay, exactly right. Let's see. I don't know if I want to put this up here and cross some stuff off. Okay, so yes, negative 5 halves is what you should have gotten there. All right, very good. And then let's go to, something we haven't heard from yet, maybe. Calculator. Oh, nope, heard from them already. All right, let's go to Noah Miller. Okay, so Noah, what did you get for number 4?
There's 1 0 at 2.
1 0 at 2, exactly right. Okay, so let me just scoot that over. There we go. Okay, so when we do our kind of method that Ms. Whitmire taught us, right, and you set that numerator equal to 0, okay, we can factor it. We factor from here, so we have x times x minus 2 equals 0. All right, set each factor equal to 0, and you get x is 0 and x minus 2 is 0. So then, I got 2 zeros here. Noah, why did I throw? Well, I can see here I threw it out too. But why did you only say 2? Why didn't you say 0 there?
Because the domain says 0 can't.
Right. Okay. And the domain restrictions, right? If we go back to looking at our function, which we did not look at for any of our earlier functions, and we didn't look at them in the earlier functions because they didn't matter. But the reason why I gave this one to you specifically is because that 0 there, okay, it's restricted from the domain, so it cannot be a valid x value in the first place, and so we just throw that out. It's not a 0, okay? And in fact, it's going to be a whole, okay? We'll talk about those kind of things later. So yeah, just x equals 2 is a 0 there, all right? So now you have to kind of be on your toes a little bit, right? We have to not only consider the zeros, but also domain restrictions and make sure that we don't include any zeros that are restricted from the domain in the first place there. Okay? Questions on anything like 3 or 4? Does that make sense? Okay. One other little thing I wanted to say here, and I didn't see anyone do this, so I hesitate to show you and put like bad ideas in your brain, but sometimes if you're like maybe not, prepared, if we hadn't already talked about the zero product property and like maybe this was like days later and, I just like throw this problem randomly at you, or you come across it in the wild, you might be tempted to add the 2x over so that you can then divide both sides by x, right, and be left with x equals 2. Which, it does give you a solution to that equation, but it doesn't give you all the solutions, right? It misses the 0, which in this case wouldn't be that big of a deal because only 2 is a 0 in the first place, but you would lose a solution there, okay? And you should always be very cautious about dividing aside by x. And the reason for that is that x, we don't know its value, and x could be 0. And so you could potentially be dividing both sides by 0, which, of course, mathematically we're not really supposed to be doing, right? So this can actually result in some very weird things. Like there's mathematical proofs, and maybe you've seen them on like Twitter or Facebook or something like that, where someone shows a proof that like 1 equals 2 or something, and you look through, you're like, no way, and you like look through the math, and you're like, all right, seems legit, kind of thing. But it's not, all right? It's not legit, and it normally has something to do with dividing by x. Okay, or dividing both sides by 0. Oh, that's one of them I've seen at least. And if you're interested, I can pull one up sometime and show it to you because it is kind of fun to see. Again, I'm a math teacher though, so my definition of fun is probably different than your definition of fun. Okay. Anyway, let's look at intervals of increasing and decreasing, and constant, and then we'll be done. Okay. So we'll look at increasing, decreasing, constant. Okay, so again, I'm not going to do any specific definitions of these things. I mean, increasing, that means it goes up from left to right, right? Decreasing, it goes down from left to right. And then constant, the function stays the same, right? The value of the function does not change. That's why we use the word constant, right? That means unchanging. So, let's just jump right in and ask, for what intervals is the given function increasing, again I'm just going to abbreviate, decreasing, or constant. And again, just like talking about the range, you have two options here. Option one, you use your calculator, okay? So, for example, we have g of x, excuse me, here, equal to like negative 2x squared plus 8x minus 7. Okay, and we want to determine that behavior. Now, you already know, right, it's a parabola. Right? And so we know by the shape of a parabola there will be no interval where it's constant, right? Parabolas are never really flat. There is an instant where it would be, unchanging, but that's an instant, right? That's not really an interval. And so we really are going to be focusing on, increasing and decreasing here. You may even be able to tell, right, because that negative 2x squared, the parabola will be, an upside down or a frowny face, right, kind of thing. So upside down from the normal shape that we see reflected. So it's going to be increasing for the first interval and then decreasing for that second interval if you go from left to right there, right? Also here you could potentially rewrite this in vertex form, by completing the square and stuff, if that's something that you prefer to do. But also we can just use a calculator here for this as well. So let's take a look. Okay, so there is its graph. And so we can see here that for the first part of the graph, from x values of negative infinity to a certain point, we're increasing. So we increase. Okay, right? We start at negative infinity. And then how can we maybe use our calculator here to determine at what x value it stops increasing? What command can we maybe use here? Yeah, change the maximum. Yeah, maximum in this case, right? Because that's going to find that highest point there. So again, we'll go to the left of the maximum, we'll go to the right of the maximum, hit enter, and then if you want to for the guess, you can move it in close to where you think the maximums are going to be approximately. And so there it is. Again, my calculator has this weird rounding error that it's giving me. It should just be 2, 1. All right, so we'll just say 2. And again, I'm not going to include that 2, because really at 2, at the instant of 2, technically it's not increasing or decreasing at that point. So that's why I'm just going to leave it excluded. And so then starting back at that 2 and then on to infinity, we know it's going to decrease again based on the graph there. Okay, so of course you got your calculators available to you at certain situations and stuff. Okay. All right. But of course there's other functions, right? So or things that we can just use transformations to help us. For example, if h of x equals the absolute value of x minus 5. Whoops. I don't know why I keep wanting to draw. There you go. Absolute value of x minus 5. Right. This takes our absolute value function and just shifts it right 5. And so 1, 2, 3, 4, 5. And so, if you can just picture it in your mind, essentially just use your mind as a graphing calculator, right? It's going to look something like that. Okay, and again, this increasing and decreasing behavior, it can mess us up sometimes. And I think I have to be careful. I give this mathematical definition. It's very precise, right? And, but it can be tricky. For example here, right, I have some students, and not that I'm saying that's, bad, I'm just saying this happens, right? When you go, it's like, oh, it's increasing, right? That arrow, it's pointing up, it's going up, it's increasing. It's like, yes, that is going up. Well, you have to be careful. The definition of increasing means it's going up as you go from left to right. You have to read it like a book, right? So left to right, we're actually decreasing here. And so it's a decrease from negative infinity to 0. And then an increase from 0 to infinity there. So again, sketch it out if you need to, right? Using your transformations, or just visualize it in your brain. That's fine too. All right, we'll do one more here. And this one I'm going to have you guys try, okay? So just try this one. please try it without a calculator. If you really need to, do it and then check with your calculator. But try this without a calculator. It shouldn't be too bad. What that graph is going to look like, or what its parent function is, and then how it transforms, right? And then where it's going to be increasing, where it's going to be decreasing, and where it might be constant. But of course, it's not going to be constant. Volunteers? Yep, Sean? Is going to be where is what behavior? Increasing from negative infinity to infinity and decreasing? Never. That's right. Okay, yeah. Negative infinity to infinity and then decreasing never. You'll notice I kind of skipped over constant here, right? Well, it's because, none of these graphs, none of these things even had a constant behavior. I guess I could have listed that and just said never. Do we have an easy graph where we are going to have some constant behavior in it? You have an idea, Robert? Yeah, like y equals 0 or like y equals 3, right? There's like a horizontal line. That's the only real, easy kind of constant behavior stuff that we see. I would think, I'm thinking of, yeah. It's like y equals a number, right? That would give us a horizontal line, so it's constant, but that's constant everywhere. So again, not super interesting because it's just the whole thing is constant. But anyway, there are some piecewise functions that you can maybe run across that would have partially, constant and partially increasing, partially decreasing, all that jazz. All right, that's it. So let me get you guys your assignment here, okay? Okay. And it's not very much homework, too, so there's a very good chance you'll get it all done here. So page 62, 41 to 45, and 121. And then page 82, number 90. Okay, and that's it. Is that it? Ooh, like you left one behind or something? I did not, or no one handed one in. So if it's not there, I'm not sure where it might be. Do you have an idea about where other places where it might be?
Might be at home.
Okay. Yeah. No. Do you need a book, or are you going to be okay?
Yeah, I can find it on
Okay.